Our presentation is on GNF gene drive genetic differences between RSV A and B. I'm Jamina,
I'm Han.
And I'm Aaron.
and we're going to go into the introduction. So, what is RSV? It is a known respiratory syncytial virus that affects the nose, throat, and lungs. It is a common respiratory virus that is hard to distinguish between the flu, or known as influenza, common cold, and COVID-19. RSV does not cause symptoms in adults, but is more common with infants and young children. RSV can lead to bronchiolitis and pneumonia. And on the right side, there's an image of the lungs with pneumonia. So, what are the symptoms of RSV? Symptoms include congestion or runny nose, low-grade fever, sore throat, sneezing, and headache. More severe symptoms are high fever, coughing, wheezing, difficulty breathing, or known as rapid breathing, cyanosis, which is bluish color on the lips, lethargy, and poor appetite. And on the right, there's a chart of the difference between the cold, flu, and RSV. RSV includes cough, stuffy or runny nose, sneezing, wheezing, fever, and again, pneumonia. Treatments include for home treatments, they include over-the-counter OTC pain relievers such as Tylenol, nasal saline to reduce congestion, prescribe antibiotics for pneumonia, and in severe cases, for if home treatments don't work, this includes intravenous IV fluids, humidified oxygen, bronchodilators, or known as inhalers, and in severe cases, ventilation. Differences between RSV A and B strains. It varies with seasonal factors such as how contagious and their symptoms. Strain A is most contagious and does not involve with vaccine development. It peaks between the months of flu season, which are November and December. Strain B is commonly mistaken by the common cold or influenza. It does not cause severe symptoms listed on the symptom slide, and both strains are still developing vaccines. And our focus on this project is to find the differences between RSV-A and B strains. So differences between G and F proteins. G gene is responsible for attaching the virus to the host cell. It is highly variable in central regions. Under strong immune selective pressure, the F gene is responsible for fusing the viral envelope with cell membranes. It maintains a critical structure to this function or is structurally conserved. And if a mutation error occurs, the F gene has difficulty delivering genetic information to the host cell. And our hypothesis is that we hypothesize that the G and F glycoprotein genes show greater sequence differences between RSV-A and B strains than other RSV genes, suggesting they are key contributors to genetic separation between subgroups.
All right, so going into the methods and how we went about our project, we first did a database search and sequence selection on the NCBI nucleotide database. Our search term used was the respiratory syncytial virus. Uh, Filters applied were complete or near complete gene sequences. 10 sequences were selected total. We specifically tried to include both F fusion and G attachment glycoprotein genes, and we tried to include RSVA and RSVB subtypes. After the sequences were selected, Table 1 was created. Original GenBank sequence titles were obtained for each RSV sample. We made simplified identifiers to make it easier to reference sequences during analysis. We just labeled these 1 through 10. After we downloaded and labeled FASTA sequences, each sequence collected was downloaded in a FASTA format that you can see on the right picture. We just clicked FASTA on the NCBI record. FASTA sequences were saved and stored for later sorting after the greater than symbol. GenBank accession numbers were also stored for BLAST comparison. To identify the RSV subgroup, each sequence was checked using NCBI BLAST. Top BLAST hits were used to determine RSV type A or B. Gene type G or F and accession numbers were recorded. Information was organized into a reference table, which is table 2, and simplified sequence identifiers were created as well. So you can see on the right side. You just clicked Run Blast from the NCBI page, and then you open the blast, and you should have the accession number automatically copied and pasted. Table 2 just kind of displayed our sequences used in the study. We again had the GenBank ascension numbers for the 10 sequences and subgroup RSVA or RSVB. And we had a corresponding glycoprotein gene, G or F, as well. When we were creating our phylogenetic trees, we first accessed genome.jp, also known as GenomeNet. We clicked on bioinformatics tools, then on the tree or the phylogenetic tree tool. Multiple sequence alignment was done using ClustalW, using methods like neighbor joining and maximum likelihood. And we just kind of pasted the fastest sequences and you clicked execute, and then your first phylogenetic tree should be complete. After we got our first one with GenomeNet, we proceeded to go to phylogeny.fr. We just copied the same 10 FASTA sequences and inserted them into phylogeny, and it helped us create a rooted phylogram. And then for the unrooted phylogram that we created here, we just scrolled down and selected radial by draw tree. Here are the figures that we created. Figure 1 is just a phylogenetic analysis by pipeline or by GenomeNet, and it just showed the comparison between all 10 sequences. Figure 2 was again a 10 sequence comparison, but now using phylogeny FR, and figure 3 was just the unrooted version of it. We also did a G gene only analysis. We repeated the phylogeny tree steps from slide 14 for only G gene sequences to allow for a better comparison, and 5 G gene sequences, which were all RSVA, were copied and submitted for the tree building. The top one is just the regular phylogram, and then the bottom version is just the unrooted one. We repeated the same steps for the F gene only analysis. Same thing, steps from slide 14, but only for the F genes. Both RSVA and RSVB strains were included here, and the rooted phylogram was in figure 6, and the unrooted was in figure 7. So results and discussion. From figure 1, we can see that figure 1 shows the evolutionary relationships among the all 10 RSV sequences. Major divergence between F fusion and G attachment glycoprotein genes is seen, and we can see a very early evolutionary split. Figure 2 shows the 10 sequence comparison of RSVF and G genes using the regular phylogram or phylogeny.fr. We can see two major clades here, or groups, separated by the RSV subtypes. The upper clade included all 5 RSVA sequences, while the lower clade included 3 RSVB and 2 divergent RSVA sequences. For figure 3, we can see the same 10 sequence comparison, however, using an unrooted version, which shows relative evolutionary distances without assuming direction. This confirmed our major separation between the F and G gene clusters. For figure 4 and figure 5, or just the G gene trees, we can see that the RSV sequence 2 is the most divergent of G genes in figure 4, and RSV1 sequence clusters with RSV sequence 4, 7, and 8. In figure 5, which was the unrooted version, we can just see that RSV sequence 2 is displayed the furthest away, and the remaining sequences cluster very closely, likely sharing an ancestor between them. For the FG gene trees, we can see figure 6 shows the upper clade of RSV sequence 5 and 10 closely related, with the lower clade showing RSVB sequences 3, 6, and 9, which highlights an early evolutionary split between RSVA and BF genes. Figure 7 is just again the unrooted version, and it shows us that RSVB sequences 6 and 9 are very closely related, 3 is a little bit more distant, and RSVA sequences 5 and 10 closely clustered together.
So, figure 2 shows a splitting of sequences for RSVA, sequences 3, 6, 9, 5, and 10 from RSV sequences of 1, 2, 4, 7, and 8. The bootstrap values between the G and F genes are at a value of 1, showing high confidence that there is an evolutionary relationship. The same can be said for RSVA sequences 5 and 10. Sequence 3 shows a bootstrap value of 79 between the sequences of 5 and 10. Sequence 7 shows a bootstrap value of 74 from sequences 4 and 8. And sequence 4 and 8 have a bootstrap value of 75. The relation between RSVA sequence 2 and sequence 7, 4, and 8 are very low at a 0.003, and the sequence of 6 and 9 are unreliable with a value of 0. Figure 4 shows RSVA sequence 7 holds a similarity to RSVA sequence 4 and 8 with a value of 80%, while RSVA sequences of 4 and 8 correlate with each other at a value of 79. Figure 6 shows that there is a clear divergence of the RSVA sequence 5 and 10 away from the RSVB sequence of 3, 6, and 9, showing high correlation with a bootstrap value of 93. Conclusion. Overall findings, the G and F glycoprotein genes show more variation between RSV A and B than other RSV genes. 10 nucleotide sequences were analyzed. 7 sequences are RSVA and 3 are RSVB. Separate phylogenetic trees were constructed for the G and F genes, showing a clear split, and there is a distinct clustering pattern observed between RSVA and B. Gene-specific observations. The G gene sequence of RSVA shows higher variability, and the F gene sequence of both RSVA and B were more closely related. What our findings highlight is a notable genetic and functional difference between RSV subgroups.
And that concludes our presentation. These are our sources. Thank you.
Thank you.
Thank you.